November 1943. The valley of the Sangro River, on the Adriatic side of Italy, where the rain had been falling for 9 days, and the river had risen to meet it. A young Royal Engineers lieutenant stood on the near bank in the dark and looked at a problem that, by every rule he had been taught, did not have a fast solution. In front of him ran perhaps 120 feet of cold brown water, swollen and moving fast, carrying with it the debris of 9 days of rain upstream. Uprooted vegetation, timber, the occasional dark shape that might have been anything. On the far side, somewhere out in the black, were German guns, registered on exactly the spot where any sane army would try to cross. Behind him, backed up along a road churned to soup by days of vehicle traffic and rain, that the road's original builders had never anticipated, sat the tanks. Sherman tanks, each one better than 30 tons, waiting to go forward, and unable to go anywhere at all. Between the tanks and the war was the river, and across the river there was no bridge, because the Germans, retreating north up the spine of Italy with the patience and professionalism of men executing a prepared plan, had blown every bridge they passed. This was the whole Italian campaign written into one river valley. Italy is a ladder of rivers laid across the only direction an invading army can travel, and the German engineers walking backward up that ladder had turned each rung into a demolition. Blow the bridge, register the guns on the gap, fall back to the next ridge, and let the geography do the killing for you. A river you cannot cross is worth more than a division you do not have. The math was that clean, and the Germans had been doing it since the Allied landings in the south, and they were getting better at it with every river they crossed. The lieutenant had been taught how armies crossed rivers like this one. You brought up a heavy bridge, a great purpose-built span of girder, and you brought up the cranes and the heavy tackle to launch it, and you brought up the trained specialists who knew how, and if the enemy was shelling the crossing you waited, sometimes for days, because a bridge strong enough to carry a tank was heavy enough to need machinery to put it in place, and machinery standing in the open at a contested river is machinery that gets destroyed. Strength meant weight. Weight meant cranes. Cranes meant time. Time at a river under registered guns meant dead men and wrecked equipment, and another day the advance did not move. That was the logic, and every army in the world, German and British and American alike, had accepted it as something close to a law of nature. So when the lieutenant turned and watched his sappers begin to unload the lorries, an officer from an older war might have wondered what on earth they thought they were doing. There were no cranes. There was no single great span of girder. What came off the trucks, piece by piece, carried by hand, 6 men to a panel, was a stack of identical steel rectangles. Lattice frames of welded steel, each one the same as the last, plain enough that you might have mistaken them for the scaffolding outside a building site. The men laid them out in the mud and began to pin them together by hand, in the dark, in the rain, while the river ran and the guns waited on the far bank for the engineers to become a target worth ranging on. By every principle of bridge engineering as it had been understood for 100 years, what they were attempting was not supposed to work. You did not carry tank load capacity across a flooded river in the backs of ordinary trucks. You did not build a structure strong enough for armor out of light parts a handful of soldiers lifted by hand. You did not throw a bridge across a contested gap in a matter of hours, from the safe bank, without ever putting an engineer in the water or on the far side. The thing those men were building broke the equation that every professional soldier had memorized, and it broke it so completely that engineers on the other side of the war would later stand over captured examples and struggle to accept what they were looking at. They had reason to struggle. That pile of plain steel rectangles was one of the least celebrated war-winning ideas of the entire conflict. A piece of equipment that a senior British commander would later credit, in flat and unsentimental language, with making the speed of victory possible, and that he said outright he could not have done without. It had no engine. It had no moving parts. It would never appear on a recruiting poster, and it did more to move the armies of the West across Europe than most of the weapons that did. Every textbook said it could not be done this way. What follows is how a civil servant with a sketch and a stack of identical steel panels proved every one of them wrong. Please hit that like button. It tells us these forgotten engineering stories are worth telling, and it helps us bring more of them to light. Subscribe if you haven't already, because there is a great deal more history of this kind that the documentaries skip straight past. To understand why the bridge mattered so much, You have to understand the bottleneck it was built to clear. Because the bottleneck was not the enemy. It was arithmetic. A mechanized army does not move on roads so much as it moves on crossings. Every river, every canal, every blown culvert and dynamited viaduct is a valve. And the rate at which an army can pass its tanks and its trucks, and its fuel, and its ammunition through those valves, sets the absolute ceiling on how fast it can advance. You can build all the tanks in the world. If they are lined up on the wrong side of a 40-foot gap of water, they are scrap with good morale. The German retreat through Italy understood this perfectly. It was not trying to hold ground for its own sake. It was trying to sell time, and the currency it sold time in was demolished bridges. A blown bridge was rarely just a delay. The far bank tended to come with guns already ranged on the only sensible crossing point, because any competent engineer on the retreating side knew exactly where an attacking army would have to put its bridge. The river did not merely slow an army down, it offered to kill whoever tried to hurry across it. A single span dropped into the water at the right moment cost an advancing army a day or more. And Italy offered a fresh river to do it at the whole length of the country. Multiply that by dozens of crossings and you have a campaign measured in months that should have run in weeks. Multiply it further by the quality of the German demolition teams, who were not improvising but executing a systematic rearguard program that had been planned in advance, and you begin to understand the scale of the problem the Allied engineers were actually facing. The trouble was that the Allied armies had walked into the war carrying bridges that could no longer do the job, and the reason was a problem nobody had fully solved before the shooting started. Tanks had been getting heavier every year, and they were getting heavier for reasons nobody could stop, because every increase in armor invited a heavier anti-tank gun, and every heavier gun invited still more armor. And the machines at the end of that spiral were far weightier than anything the old bridging tables had been written for. The light machines of the late 1930s had given way to medium tanks of 30 tons and more, and the heavy designs coming up behind them were heavier still. A bridge is the one piece of equipment that has to be sized for the heaviest vehicle in the whole force. So every ton a new tank put on quietly raised the bar for every bridge an army owned. The British had entered the war leaning on equipment like the Inglis Bridge, a tubular steel truss whose basic concept dated back to the First World War, and the engineer Charles Inglis, and on a family of box girder bridges that were sound enough in their day. Their day was ending. Some of these bridges were too light to take the new tank weights at all. The ones that were strong enough were monsters to handle, great rigid spans that had to be assembled more or less whole and then heaved into position with heavy launching gear, which meant cranes, which tied up specialist troops for long stretches, which meant time, which meant exactly the kind of large, slow, conspicuous operation that a contested river crossing cannot afford. The equipment that worked in a slower war was being defeated not by enemy action, but by the increasing weight of its own army's vehicles. This was the equation in its cruelest form. To carry a heavier tank, you needed a heavier bridge. To launch a heavier bridge, you needed heavier machinery. Heavier machinery at the riverbank took longer to set up and was easier to destroy. And so the very thing that made a bridge useful, its strength, was the thing that made it slow and vulnerable to put in place. Engineers on every side of the war had stared at that equation and concluded it could not really be broken. You could refine it. You could optimize around its edges. You could not escape it. A strong bridge was, by its nature, a heavy, slow, complicated thing to build under fire. And that was simply the price of crossing rivers in a mechanized age. There was a particular urgency behind all of this, in the first years of the war, and it came from hard experience. The British Army that came home from France in 1940 had left most of its heavy equipment behind on the beaches at Dunkirk, and was building itself back up from a thin base, and the tanks it was now building were heavier than the ones it had lost. The requirement for a bridge that could take the new weights and still be put across a gap quickly was not a peacetime exercise in gradual improvement. It was a live and pressing operational need, the kind of need that occasionally shakes a stagnant problem loose and lets a genuinely new answer through. The old bridging had been good enough for a lighter and slower kind of war. The war that was actually being fought was heavier and faster than anything the existing equipment could properly serve, and the men responsible for bridging knew it. The man who broke the equation was not a tank commander or a frontline engineer who had watched men die at a river crossing. He was a civil servant. Donald Coleman Bailey worked for the British War Office at a place called the Experimental Bridging Establishment in Christchurch, on the south coast of England. It was exactly the sort of unglamorous government outfit that the histories of the war tend to skip. A collection of engineers and draftsmen whose job was to test bridging equipment and argue about load tables in a series of unremarkable buildings, while the larger drama of the war played out elsewhere. Bailey was not a famous man, and he did not become one in the ordinary way, which is part of why the bridge that carries his name is far better known than he ever was. Bailey was quiet and methodical, a man who had spent his career thinking carefully about how steel carries weight, and he had been turning over an idea that ran directly against the accepted wisdom of his profession. The wisdom said that a strong bridge had to be a single, large, carefully computed structure, and that small repeated parts made a weak bridge fit for footpaths and light pedestrian traffic, and not much else. Bailey thought the wisdom had it backward. The story that gets told, and it is the kind of story that may well have been polished in the retelling over the years, is that he first sketched the concept on the back of an envelope, working out the basic geometry of a repeating truss panel on whatever was closest to hand. Whether or not the envelope is literally true, the idea on it was the thing that mattered, and the idea was almost insolent in its simplicity. Everyone else was trying to build a better big bridge. Bailey proposed to stop building big bridges at all. Instead of one large purpose-made structure, sized and shaped for a particular gap and a particular load requirement and a particular set of ground conditions, he proposed a kit, a set of small, identical, interchangeable parts that an army could carry around in ordinary military trucks and assemble into whatever bridge the moment required. The heart of the system was a single component, a welded steel lattice panel, a rectangular frame of crisscrossed steel members, braced and triangulated to carry load efficiently. Every panel was the same as every other panel. They pinned together, edge to edge and end to end, with steel pins driven home by a man with a hammer. There were no special joints, no tapered sections, no components that were unique to a particular position in the structure. No part of the system was precious. If a panel was bent by a shell fragment, or dropped in a river, or lost on a muddy road somewhere in Italy, you reached into the truck for another one, because they were all the same, and there were hundreds of them. That was the thing the professionals could not at first accept. A bridge built out of small, light, repeated parts ought to be a weak bridge. The intuition of a century of engineering practice said that strength came from mass and from the careful, integrated design of a single structure in which every member was computed for its exact position and its exact load. A pile of identical lattice frames, bolted together in the field by ordinary soldiers, looked like a recipe for a footbridge at best, something that might take a man on a bicycle in good weather. The skepticism was real, and it was not confined to one army or one tradition. German military engineering in particular came out of a tradition that prized the permanent, the heavy, and the properly calculated. German engineers were superb at what they did, and what they did was build bridging that was solid, deliberate, computed to the last decimal, and designed to last. The notion that you could match tank load capacity by stacking up light, mass-produced scaffolding, assembled by ordinary soldiers from the wrong bank of a contested river, ran against everything that tradition assumed about how a serious bridge was supposed to come into being. It looked, to a properly trained engineer of that school, like it should not work. Which is exactly why it took the better part of the war, for the people on the receiving end to believe what they were seeing night after night across the rivers of Italy and France. The reason it worked is worth slowing down on, because the cleverness was not in any single piece. It was in the system, and the system inverted the old equation instead of merely improving it. Start with the panel itself. It was about 10 feet long and a little under 5 feet high, a flat rectangle of welded steel lattice, and it weighed something in the region of 600 pounds. That is a heavy object by ordinary standards. It is not, however, a heavy object in the way a crane-launched girder is heavy. It was light enough that 6 men could pick one up and carry it between them, walking in step. And that single fact changed everything that came after it. Because the panel could be carried by hand, the bridge did not need a crane. Because it did not need a crane, the entire slow, conspicuous, and vulnerable business of bringing heavy lifting machinery up to a contested riverbank simply disappeared from the equation. The men were the machinery. A bridging team and a stack of panels on trucks could accomplish what had previously required a crane, a specialist launching set, weeks of additional training, and a great deal of standing in the open, waiting for things to be rigged and heaved into position. Then comes the part that broke the strength problem, and it is genuinely elegant in the way that the best engineering solutions tend to be. Not complicated, but clean. The panels could be assembled side by side and stacked on top of one another. One line of panels gave you a light bridge, adequate for infantry support vehicles and light trucks. Set 2 lines of panels alongside each other, and you doubled the lateral strength. 3 lines, and you tripled it. Then you could do the same thing vertically, building the trusses 1 story high, 2 stories, or 3 stories, each additional layer adding to the load-bearing capacity of the whole structure. Combine the 2 dimensions and you had a whole family of bridges. From a single line of single-height panels suitable for infantry and light-wheeled traffic, all the way up to a triple-wide, triple-high truss that could carry the heaviest armor the Allies owned across a serious gap in a flooded river. And every single one of those bridges was built from the same identical part. You did not design a new bridge for a new problem. You did not order special components and wait for them to arrive by specialist transport. You matched the bridge to the river and to the load requirement by adding more of the panels you already had sitting on the truck behind you. Strength came not from a stronger part, but from more of the standard part, applied systematically. That is the sentence that engineering doctrine across multiple armies found so hard to absorb, because it took the thing that was supposed to make a modular bridge weak, the repetition of a small, light, undistinguished component, and turned it into the source of strength. The third piece of cleverness was how you got it across the gap, and this was the part with a soldier's life riding most directly on it. You did not float the bridge out on the water and wrestle it into position from boats. You did not build it by standing in the river and working both banks simultaneously while enemy fire reached for the men in the water. You assembled it on rollers, on your own bank, the safe bank, lying flat and pointing at the far side. Out in front of the main bridge structure, you built a lighter section called the launching nose, a long tapering feeler made of the same panels, lighter and less substantial than the bridge proper, because its job was not to carry traffic, but to reach across the water and find the far bank. Then you pushed the whole assembly forward on the rollers, out over the gap, as a cantilever, with the launching nose reaching ahead across the water, while the massive bridge behind it held it down and kept it balanced against the pull of gravity. The men kept building new panels onto the tail of the bridge as the nose crept forward, maintaining the balance of the cantilever, until the nose touched down on the far bank. Once it was across and bearing on the ground, you removed the launching nose, jacked the finished bridge down off its rollers and onto firm bearings at each end, laid the timber decking, and it was a road. The crew building it stood on their own side of the river the entire time. Nobody had to swim a line across under fire. Nobody had to work on the enemy's bank to catch the far end of a span. Nobody had to be in the water during the most dangerous phase of the operation. You launched the bridge from the cover of your own bank and let it walk itself across the gap on its own geometry. For an army crossing rivers that the enemy had pre-registered with artillery, that single feature was worth more than any amount of raw load capacity, because it meant the most dangerous ground, the far bank, did not have to be held or even approached by an engineer until the bridge was already reaching it. It is worth picturing the build itself in detail, because the rhythm of it captures what made the whole system different from anything that had come before. The bridging team laid a line of rollers along the home bank, square to the river and level as the ground allowed, and began assembling the first panels of the bridge on top of them, lying flat and aimed at the far side. Panels went up by hand, one after another, carried to the assembly point by 6-man parties and pinned together with steel pins driven home by hand. The structure grew backward, away from the water, as the men added panels to its tail. Ahead of the leading edge they built the launching nose, lighter and tapering, extending out beyond the main bridge structure and reaching toward the gap. Then they pushed. The whole assembly rolled forward on the rollers, the nose reaching ahead into empty air as a cantilever, while the accumulating weight of bridge behind it held it down and kept it from tipping into the river. The men kept adding panels at the tail and kept pushing, and the nose crept across the gap foot by foot, the men watching it reach out over the black water, until it dropped and touched down on the bank opposite. Once it was across and bearing, the team jacked the bridge down off the rollers and onto its bearings at each end, stripped off the launching nose, laid the decking across the transoms, and opened the road. A practiced crew, working in daylight on prepared ground, could carry the whole sequence through in a few hours. Working at night in mud and rain under intermittent shell fire. It took longer, but it could still be done in a fraction of the time that any previous equivalent would have required. And it could be done without a single piece of lifting machinery services. The same kit did a great deal more than throw quick tactical spans across contested rivers. The panels could be built up into fixed bridges on proper pier foundations. The kind of solid, lasting crossing an army needs once a front has moved on, and the supply traffic has to keep flowing across the same river for weeks or months. They could be carried on floating pontoon supports, each pontoon holding up a section of paneling, to cross water far too wide for any single clear span. The longest Bailey crossings of the war, some of them thrown across great Asian rivers in Burma, ran to lengths that would have astonished anyone who first encountered a stack of 10-foot panels on a truck. And because the parts were pinned together, rather than welded permanently into place, a bridge could be taken apart again. An army that had thrown a Bailey across one river could, when the advance moved forward and that river was no longer a front-line concern, dismantle the bridge, load the panels back onto the trucks, and carry them forward to the next river to build all over again. The same panels might cross 3 different rivers in 3 different months, as the campaign moved north. The bridge was not only fast to put up, it was reusable, a rolling inventory of crossings that traveled with the army and got used again and again, which multiplied the value of every panel ever manufactured by a factor that the raw production numbers alone cannot convey. Wrap all of that in the logistics, and you begin to see why it changed a war, rather than merely improving a piece of equipment. Every component was standardized and interchangeable, which meant any steel mill in Britain or America or Canada could turn out panels by the thousand to a single drawing, and a panel made in Sheffield would fit perfectly against one made in Pittsburgh or Toronto, because they were all made to the same specification. The parts were sized to ride in standard military trucks, so the bridge traveled with the army, rather than lagging behind it, in some slow-moving specialist train, waiting for roads to clear. And because the assembly required no special equipment, and was a matter of carrying panels, lining them up, and driving pins, it could be taught to relatively ordinary troops with a manual and sufficient practice. You did not need a small priesthood of bridge-building specialists for every crossing. You needed trained engineers to supervise and run the job, certainly. The muscle work could be spread across many more hands than the old heavy bridges had ever allowed. Stand back from all of that, and look at what they had actually made, and the thing is almost comic in its plainness. The secret weapon, the war winner, the object a field marshal would say he could not have advanced without, was a flat steel rectangle, with no moving parts, that a corporal could bolt to another flat steel rectangle, with a hammer and a pin. It had no engine to fail, no electronics to short out, no precision mechanism to foul with Italian mud. It would not have looked out of place holding up the scaffold on a building under renovation. And it did more to carry the armies of the West forward through Europe than a good many of the tanks it carried, because the tanks were only ever as useful as the next river allowed them to be, and the next river, again and again, was crossed on a stack of these unglamorous panels. Italy was where the Bailey Bridge stopped being a clever concept proven on a test course in Christchurch and became the operational backbone of an advancing army, and Italy was the perfect, terrible laboratory to prove it. The country could have been designed as a test course for bridging. An army moving up the peninsula has to cross river after river after river. The terrain ensures that these are not wide, shallow, fordable affairs. The rivers run fast and cold between steep banks, channeled by the ridges on either side into obstacles that stop wheeled and tracked vehicles with equal finality. The Volturno, the Sangro, the Rapido, the Gari, the Liri, the Arno, the Po, each one a defensive line as long as the river itself, each one handed to the retreating Germans as a gift by the geography of the country they were defending. The German rearguard, retreating in good order from one prepared defensive line to the next, blew the bridges over every one of them. This was not panic demolition carried out by frightened men running from an advancing enemy. It was a deliberate, professional, unhurried program of destruction, executed by men who knew exactly what they were doing and had prepared for it carefully. The German engineers in Italy were skilled and well supplied with demolition equipment, and they had had time, in many cases, to pre-charge the bridge foundations before the Allied advance even got close. When the moment came to fall back, the bridge came down cleanly, completely, and at exactly the right time to impose the maximum delay on whoever was trying to follow. Each blown span was not just a structural problem for the Allies. It was time purchased for the German defense, time to improve the next ridgeline, time to bring forward ammunition, time to register the guns on the crossing site and wait for the engineers to show up in the dark. Against that program, the Allied engineers ran their bridges out as fast as the rivers came. At the Volturno, in October of 1943, with the autumn rains beginning and the river running higher than the seasonal average, the engineers crossed in multiple places simultaneously. Throwing Bailey spans across a river, the Germans had assumed would stop the advance cold for at least several days. At the Sangro the following month, in the mud and rain that had made the river valley almost impassable for wheeled vehicles, the crossings went in under shell fire, at night, in conditions that made every physical task twice as difficult as it would have been on a dry day in peacetime. At the string of crossings around the brutal fighting at Cassino, where the Rapido River became one of the most costly river assaults of the entire war, the Bailey spans were central to keeping supply and support moving across the water, while the infantry paid the price of the far bank in blood. And eventually, far to the north at the Po, the crossing that opened the last phase of the Italian campaign and sent the German armies in Italy toward final collapse, the engineers had the spans across before the German command had fully registered that the assault had succeeded. The pattern was always the same in its broad outline, however different the specific conditions. The Germans would blow a bridge and fall back to the next ridge. The Allied advance would close up to the river, and the infantry would secure the near bank. And then, often after dark, often in weather that made the work harder and the footing uncertain, often with German guns reaching for the crossing site because the enemy knew where the bridge had to go, the trucks of panels would come down to the bank and the sappers would begin to build. A bridge that might once have taken the better part of a week went up in hours. Crews competed, in the particular way that men under sustained pressure compete when the stakes are obvious to everyone, to bring their spans in faster than the unit building the crossing next to them. The competition was not a sporting matter. Every hour shaved off a crossing was an hour the armor was rolling forward instead of sitting cold on the bank. It was also an hour less that the engineers stood in the most accurately targeted spot on the entire front. The work was as hard and as dangerous as anything in the Italian campaign, and it is the part of the story that gets left almost entirely out of the account when the account is organized around armor and infantry and the decisions of commanders. Building a bridge across a flooded Italian river in November is miserable, even without anyone shooting at you. The water runs cold and fast and carries debris that can knock a man off his feet in the shallows. The banks are mud that gives underweight and pulls at boots and coats every surface with a cold gray paste that makes every handhold slippery. The panels are heavy, and 6 men sharing the weight of one on a muddy slope descending to a river in the dark have to move in coordination and cannot afford the kind of stumble that lands one of them in the current. The pins do not always want to go. Steel on steel in the cold requires force and precision simultaneously, and cold hands on cold steel in poor light do not reliably provide either. A man with numb fingers in the dark, lining up 2 holes in a steel panel that weighs more than he does, is a man one slip away from a crushed hand or a fall into water that will not give him back to his unit. Add to all of that the knowledge that the enemy knows precisely where you are working, because there are only so many places on any given river where a bridge can cross, and a competent enemy has identified those places weeks ago and registered his guns on them, and you begin to understand what was actually being asked of the men who built these crossings. The sappers did not get to shoot back. They got to keep building while the rounds came in on the crossing site, because the bridge was the mission, and a half-built bridge crosses nothing and serves no one. There is a particular and recognizable type of humor in the way engineers who did this work have always talked about it. The flat, understated, matter-of-fact humor of men who decided that the only sane response to an impossible situation was to get on with the task and not think too carefully about the water or the distance the next round landed from where they were standing. Plenty of those men carried that humor for the rest of their lives, because the alternative was to carry something considerably heavier and less useful. Picture one of those crossings as the men who built them knew it. The trucks come down to the river after dark, lights hooded or off entirely, the drivers navigating by memory and by the white engineer tape laid through the mud to mark the approach route. The panels come off the trucks by hand, and go to the water's edge on the shoulders of 6-man parties, moving carefully in the dark, each party working in the low rhythm of men who have done this before and know what it costs to rush it. The work starts on the rollers in the cold, while a sergeant somewhere keeps up a low, flat commentary to hold the pace steady, calling the pinholes, calling the push, keeping the rhythm from breaking when a man's hands fail him or a panel binds on a roller in the mud. Now and then the German guns find the crossing site. The men flatten into the mud or keep working, depending on how close it falls, and then they go back to the panels. Because the bridge does not build itself, and the armor sitting on the road behind them does not move until it is built. A panel slips, and a man swears, and another man takes the weight without being asked. The launching nose creeps out over the black water, inch by foot, reaching into the dark over the sound of the river. Somewhere upstream, a German flare goes up and hangs in the rain, and turns the river white and flat for a few seconds. And every man on the crossing site freezes in the sudden light. And then the flare dies and the dark comes back harder than before, and the work goes on. And sometime before the light comes back, the nose drops and touches the far bank, and the bridge comes down onto its bearings. And the decking goes on, and the first tank edges up to the near end, with its engine at idle, and rolls out across a road that was a stack of identical steel rectangles on a truck 4 hours earlier. That happened, in one form or another, on river after river, the whole length of Italy. It is not the sort of thing that appears in newsreels. It is exactly the sort of thing that decides campaigns. This is also the point in the story where the bridge stopped being a purely British piece of equipment and became, in any honest telling, an Allied workhorse, built to a scale that only American industrial capacity could provide. The design was Bailey's, and it came out of that establishment in Christchurch. But the United States adopted it early, mass-produced it, and used it on a scale that in volume terms dwarfed the original British production runs by a significant margin. American steel mills turned out the panels by the trainload. American engineer units in the United States Fifth Army built Baileys across the same Italian rivers as their British counterparts in the Eighth Army, often within sight of each other's crossing sites, the two armies solving the same problem with the same answer simultaneously. As the war continued into its later phases, the United States made the design thoroughly its own, refining it into a standardized American version, adapted for American manufacturing methods and American logistical systems, and pouring it into every theater where American engineers had to cross water that a retreating enemy had ruined. The bridge was British in origin and American in scale, and both of those facts are part of why it mattered as much as it did. One country had the idea and proved the concept under fire. The combined industrial capacity of the alliance turned the concept into a quantity of identical, interchangeable parts that no demolition program, however professional and however well prepared, could keep up with. The Germans could blow bridges faster than any single army could replace them by traditional methods. They could not blow bridges faster than a modern industrial alliance could manufacture the panels to replace them with a system that took hours rather than weeks. That last point closes the loop on the larger strategic story, because Italy proved something that went beyond the merits of any single bridge design. It proved that the German strategy of buying time through systematic destruction of crossings rested on a false assumption embedded so deeply that nobody on the German side had thought to question it. The assumption was that destroying a crossing created a delay roughly proportional to the difficulty of replacing it. Blow a large bridge, the calculation went, and you impose a large delay, because a large bridge is a substantial and time-consuming thing to rebuild. The Bailey severed that proportionality entirely. It did not matter how thoroughly the Germans destroyed a bridge, because the Allies were not going to rebuild that bridge. They were going to place an entirely new one beside the wreckage, out of parts they had been carrying on their own trucks, in hours rather than days. The delay the Germans were paying such high prices to impose kept shrinking, river after river, until it was measured in hours rather than days. And a strategy built to sell days that is only producing hours is a strategy that has already failed on its own terms, whether or not the people executing it have been told. From Italy, the bridge went on to do the same work on a continental scale in northwest Europe, and the rivers there were bigger, and the stakes were higher, and the pace of the advance placed even greater demands on the engineers, trying to keep the crossings open behind an armored thrust that consumed bridges the way it consumed fuel. After the Normandy landings and the breakout that followed in the summer of 1944, the Allied armies poured east across France and into Belgium and the Netherlands, and they ran straight into the same fundamental problem at greater size and greater speed. The retreating Germans blew bridges across France and Belgium and Holland as they fell back toward their own border, and the Allied advance, fast and fuel-hungry and stretched dangerously thin on its supply lines, depended on engineers throwing crossings up behind it as quickly as the enemy could tear them down. The Bailey was the standard answer at every one of those gaps, each span keeping the armor and the trucks and the ammunition moving in the direction that mattered. The bridge ran through the most famous bridging operation of the whole war. The airborne assault into the Netherlands in September of 1944 was, at its heart, a gamble on bridges, a bet that lightly armed paratroopers could seize and hold a sequence of river and canal crossings, long enough for an armored column to drive up a single road and across all of them to the Rhine at Arnhem. The bet failed at the final bridge, for reasons that have filled libraries since. Too much optimism, too little intelligence about what was waiting on the far bank, and SS Panzer units resting in the precise area the plan assumed would be clear. But underneath the drama of the seized and contested spans, the unglamorous engineering went on. Because where bridges were lost or destroyed, the Bailey was the tool that put new crossings in their place. The grand plan turned on the great existing bridges. The grind of keeping the corridor alive turned, as it always did, on panels coming off trucks and sappers working without sleep. And then there was the Rhine. The Rhine was the last great water barrier in front of the German heartland, the river the entire Western campaign had been building toward since the Normandy beaches. When the Allied armies forced it in March of 1945, they crossed on assault boats, pontoons, captured bridges, and engineered spans on a scale the war in Europe had not previously seen. The Bailey was central to all of it. Engineers built long spans across the Rhine. Some carried on floating pontoon supports to reach the full width of the river, where no single truss could span the gap, throwing roads across the last barrier between the Allied armies and the German interior, while the far bank was still being fought over. The same principle that had worked on the Sangro in the rain of November 1943 worked on the Rhine in the early spring light of 1945, multiplied by the width of the water and the weight of everything that had to cross it. More panels, more pontoons. The same method. Europe was only part of where the bridge went. In the Burma campaign against Japan, Allied engineers faced rivers that made the waterways of Italy look modest. The great rivers of Burma run wide and fast, fed by monsoon rainfall on a scale that European rivers rarely approach. And the problem they presented was not the tactical problem of a blown span across 120 feet of cold Italian water. It was a problem of sheer width, of crossing distances that no single clear span could address. The monsoon season alone could raise a river by 30 or 40 feet and spread it across a valley floor so wide that the far bank was barely visible from the near one. In that environment, the standard Italian solution of a single truss, thrown quickly across a contested gap, was simply not the relevant problem. The relevant problem was how to put a road across something that looked less like a river than like a temporary inland sea. The Bailey went to work there on a scale the European theater rarely matched. Engineers linked panels across floating pontoon supports, each pontoon holding up a section of roadway, the whole assembly stretching out across the water in a line that kept going long after a European crossing would have been complete. Some of the longest military bridges built anywhere during the entire war were thrown across those Burmese rivers, using the same standard panels and the same standard method, adapted by scale rather than by principle. The same 10-foot panel that crossed the Sangro in the dark of November 1943 crossed rivers in Burma that took minutes to cross, even by powered boat. The same geometry, the same pin, the same 6 men carrying the same component to the water's edge. On the other side of the world, in heat and monsoon rain instead of Italian mud, building the same answer to the same fundamental problem. By the end of the war, the bridge had been produced in quantities that resist easy summary. The equivalent of tens of thousands of spans worth of identical panels had been turned out by the factories of the Alliance and pushed forward to wherever an army had to cross water that an enemy had ruined. There was almost no theater of the war in which the Bailey did not appear, and almost no kind of crossing the combination of panels, transoms, decking, and pontoon supports could not be configured to make. Which brings the story back to the engineers on the other side of the war, and to what it actually meant to say that the bridge defied combat logic. The German engineering tradition treated a military bridge the way it treated most serious engineering, as a problem to be solved correctly. A bridge should be calculated for its specific task, purpose-built to the load and span requirements of the situation, constructed by qualified engineers, and made as permanent as the tactical situation allowed. There is real merit in that view. It produces structures you can trust completely, designed to their exact requirement with no ambiguity about their performance under the loads they were built for. But it carries an assumption embedded so deeply in the tradition that nobody on that side of the war thought to examine it. That a stronger bridge must necessarily be a more substantial, more deliberate, more individually engineered object. Bigger load means bigger structure. Bigger structure means heavier components. Heavier components mean cranes. Cranes mean time. Time at a contested river means dead men and wrecked equipment, and another day the Advance does not move. The Bailey came out of the opposite instinct, and it was the instinct that won. It treated a military bridge not as a permanent structure to be engineered toward perfection, but as a temporary, recoverable commodity to be thrown across a gap, used hard for as long as the tactical situation required, and then either recovered for reuse somewhere else, or abandoned as the Advance moved on. It did not try to be the right bridge for this river and this load requirement. It tried to be a good enough bridge for any river and any load within its scaling system, built from a part so standardized and so plentiful that the question of any individual crossing almost stopped mattering. The bridge became the system, and the system could not be exhausted by normal rates of consumption. What the German engineers were seeing when they stood over captured Bailey examples and struggled with the load tables was not bad engineering that had gotten lucky. They were seeing the consequence of a different question being asked at the beginning. Not how do you build the strongest bridge, how do you make the most crossings most quickly, with the least specialized equipment and the fewest constraints on where and when it can be built. The answer to the first question was a better girder. The answer to the second was a panel you could carry in a truck and pin to another panel in the rain. The deeper lesson deserves to be stated plainly, because it runs through the whole engineering story of that war and past it. The Allies did not beat the German demolition program by building bigger machines to repair bigger wreckage faster. They beat it with a better idea about what a bridge could be, and then they backed the idea with the industrial power to produce it by the tens of thousands. The Germans poured genuine skill into the systematic destruction of crossings, on the assumption that destruction buys time, proportional to the scale of what is destroyed. Blow a large bridge and you impose a large delay. The Allies quietly made that assumption false. River after river, the time penalty of a blown bridge shrank towards something the German strategy had never planned for, because the answer was no longer to rebuild what was destroyed, but to carry the replacement in the trucks and assemble it on the spot. The more thoroughly the enemy destroyed, the more completely a system built around standardization and speed proved its advantage. Escalating the destruction was not a winning move against an opponent who had stopped playing the rebuilding game entirely. The man who started it lived to see what he had done. And Donald Bailey was knighted after the war, becoming Sir Donald Bailey, the civil servant from Christchurch recognized by a country that understood, even if the wider public never quite did, what that stack of plain panels had been worth. He had not designed a weapon. He had designed the thing that allowed the weapons to get where they were needed. And in a mechanized war that turns out to be much the same thing as designing the conditions for victory. The praise that mattered most came from the men who had commanded the armies the bridge carried. The most senior British field commander of the campaigns in Italy and Northwest Europe said in plain words that across both of those long campaigns, he could never have maintained the speed and the tempo of his advance without Bailey bridging in large supply. A field marshal, looking back over armored thrusts and river battles and the long drive into Germany, with all of the weapons and technology and air power available to him, picked out as the thing he could not have done without a bridge, with no engine, that a handful of sappers bolted together with a hammer in the rain. The bridge belongs in particular company from that war. The unglamorous machines that mattered out of all proportion to their fame. The Jeep, the transport plane, and the Bailey Bridge, which put roads across rivers faster than an enemy, built to destroy them, could keep up. None of those things looked like a war winner. All of them were, precisely because they were plain and plentiful and reliable, when the elaborate and the purpose-built would have failed. When the shooting stopped, the Bailey did not retire. Armies kept it in service for decades. So did civilians. When floods washed out bridges and earthquakes dropped spans, the answer for years and years was a structure descended directly from those wartime panels, trucked in and assembled by hand and carrying traffic within days. The basic concept became the permanent template for military and emergency bridging in most of the world's armies and relief agencies. Every modern panel bridge that goes up after a flood or an earthquake is a grandchild of the thing that crossed the Sangro in the dark of November 1943. Built by men who had decided that the only sane response to an impossible situation was to keep pinning panels together and not look at the water too long. That is the legacy that outlasted the runways and the harbors and the front lines. Not a bridge, but a doctrine disguised as a pile of steel. The principle that you can beat a stronger, heavier, more deliberate solution with a plainer, standardized, mass-produced one. That good enough and plentiful and fast will defeat perfect and rare and slow in a long war fought across a continent of rivers. That the way to win the engineering war is to carry your answer with you in ordinary trucks, rather than to rebuild the enemy's wreckage with specialist equipment that arrives 3 days too late. The German engineers built bridges designed to outlast the campaigns that required them. The Allied engineers built bridges designed to outlast the next river, and not one crossing further. Only one of those turned out to be the right ambition. If you have been watching this channel for a while and still have not subscribed, now is the moment. Hit the button, turn on the notification bell, and join us. We are here with the military history stories that deserve to be told straight, without softening what was hard, and without forgetting what was, in its own unglamorous way, exactly right. Thank you for watching. Respect the fallen, honor the veterans, and never forget what they were fighting against. We will see you in the next one.